So this is another one where I spent a lot of days before I realized, yes.
Is it because that guy got input from 4 different convolution?
Pretend we already took into account, okay, summation. Still, how can we get 12 by 12 from an 8 by 8? See, the previous one was, how do we get 5 by 5 from an 8 by 8 and a 12 by 12, which was easy. Do convolution on this 12 by 12 with 8 by 8 and we'll get 5 by 5, so we'll know the gradient for the kernel. Now I want to know the delta over here so that I can keep working backwards. So the only 2 sizes involved are 8 by 8 and 12 by 12. Okay, so let me give you the answer. So it took me many, many days when I was learning it first to figure it out. Okay, and the answer is not trivial. Okay, so once again, that's why I think the Nobel Prize is justified. Okay. Okay, so there's a concept called inner convolution. And there's a concept called full or outer convolution. Okay, so let me explain what the difference is through a very simple example. Suppose I have an 8 by 8 matrix. Suppose I have a 3 by 3 kernel. Okay, so remember, so the normal convolution that we have discussed so far is the inner convolution. Okay, so if I did the inner convolution with a 3 by 3 kernel, what will be my answer?
6 by 6.
6 by 6. Okay. Now the way outer convolution works is, okay, so pretend this is 8 by 8. Okay, so extend it by, let me see, 1 or 2. Okay, let's pretend, okay, let's extend it by padding zeros over here.
So it will be 12 by 12.
Okay, so 3 by 3, if I go,
It will give you 10 by 10.
10 by 10.
yes.
In our case, it's a 5 by 5, so that's why you need 2 on each side.
Yeah, we need 2 each size over here.
So it
So,
will be 5
so
by
anyway,
5.
so basically, if we pad it by zeros, right? So this will become 10 by 10. Now if we did the, no, we have to pad it more.
We need kernel 5 by 5.
Based on what you have on the table, it's correct, but in our case, it's a 5 by 5.
Yeah, I'll come to our case, but first let me see if I can explain it. See, let's say I have a number 5, let me pick a real example, 4, 3, 2, 1, right? So normally 6, 7, 8, 1, 9, 5, and so on. Okay, so normally when we do the convolution, remember we'll put the kernel right here, multiply and add, then move the kernel 1 pixel to the right. Okay, so the first value that it produces will be in this spot. You guys agree? Okay, now with the full convolution, the way it works is we put the kernel in this spot. Okay, and whatever the kernel value is, let's say was 0.2 over here. So what's the answer will produce? 5 times
5 times
0.2.
2 point.
Everywhere else, pretend it's 0. So pretend we extended this blue thing, everywhere else is 0. So now this answer that it's producing, as you can see, will now be put
Padded with
in this spot. So if this was 8 by 8 to begin with, after we do this, what will be the
10 by
resulting
10.
size of the convolution?
10 by 10.
It will be 10 by 10 convolution. Okay, so in our case, now hopefully you'll get the idea. We have 8 by 8, right?
Yep.
And on this side, we have 12 by 12. Kernel that we applied going further forward was 5 by 5. So if I did a full convolution of this,
Yep, K into.
You get 4.
So it will
so
be-
it will give us a 12 by 12.
Yeah.
Okay, but which one will be rotated? It's not just a straight, just do the convolution. So if we again follow our math equations properly, it will tell us exactly which one will be rotated. And that's what I put in the detail of the
What is the formula for size for the outer convolution?
it will be plus the kernel minus 1. So 8 by 8 plus 5 by 5. So 8 plus 5 minus 1 will give you the 12. Okay, so anyway, I'll have you verify my equation later, but let me just quickly show you the result. Okay, this one we already did. Okay, so again, if you go through my forward pass equations, so to save time, let me leave it for you to review and verify. Okay, so this is 12 by 12, like we discussed, right? This was the next layer, the layer 2, where we had the 8 by 8 delta, right? Okay, so if you go through it, basically now we have to rotate the kernel by 180 degrees, then do the convolution. Then we will get the delta in the previous layer, okay? So these rotations are extremely important. Like I said, if you don't do them, you will never be able to get this to work properly, okay? So let me summarize, okay? So our goal was basically, we wanted to find the gradient of the K1M of 1, and there were 4 kernels involved over here, right? We wanted to find the gradient of the kernel Mn of 2. There were 6 kernels involved over here. We wanted to find the gradient of W1, gradient of W2, gradient of B1, gradient of B2, right? And of course, there are biases involved over here, biases involved over here, because there was a same bias adding to the result of the convolution. Okay, so if you go through the handout, step by step, I've given you exactly how this will be calculated, how this will be calculated, and the rest of it. And then this is what will translate to the code to build it. Okay. So anyway, remember once we, let's say this is our image, we did a convolution. So this was 28 by 28, this was 24 by 24, right? Then if you remember, what were we doing over here? What were we adding to it? Bias. And there's the same bias being added to all the elements, all the 24 by 24 elements, right? So on the backward pass, it turns out, once you wanted to know the gradient with respect to bias, it's, if you recall from our previous straightforward neural network, the bias was the same as the delta. Okay, but because it's being shared by all the convolution data, there's a summation that's involved that gives you a single number for the gradient, okay? So please try to go through it, like I said, especially as our expertise develops, we'll be creating some sophisticated architectures ourselves. So if we don't have this background, we wouldn't be able to get to that part, right? Okay, so let me give you a short break. And then after the break, I'll cover another very, very popular convolution architecture called the Siamese and the triplet networks and show you how we build them, how we implement them.